In this presentation, I will demonstrate how to perform hierarchical regression in SPSS. So the aim is to learn which steps to follow in SPSS and how to interpret the SPSS output. The example we'll use in this demonstration comes from the research on the advertisement that received plenty of complaints and was eventually banned from public spaces like underground. And suppose we have assessed people on their attitude towards the advert, their levels of self-esteem, and their perceived media pressure. What we want to know is how much media pressure affects these negative attitudes towards the advert. But we know that self-esteem has a preventative effect on this negative attitude towards the advert, and also it's negatively correlates with media pressure. So we want to control for the effect of the self-esteem and just look at the unique contribution of media pressure towards formation of negative attitudes towards the advert. So we'll do a hierarchical regression because it allows us to control for self-esteem. In terms of the assumptions, all the assumptions for hierarchical regression are the same as for multiple regression, and all the assumptions are tested as part of the regression analysis. So let's have a look at the data. So we have our participants in different age groups, their ethnicity. All participants were females, so gender was not recorded. And we have perceived media pressure, self-esteem, and attitude to advert. So to perform hierarchical regression, go to Analyze, Regression, Linear. And we put our dependent variable in the dependent box. So negative attitude to advert is the dependent variable. So the independent variable, and in here you see it says block 1 of 1. So that's where we can enter variables and steps. So the first variable we enter is the one we want control for, which is a self-esteem. Then we go next. And we can enter in our next block our media pressure scores. So, and the method we're using is enter because we just entering variables based on our understanding of the relationship between all three variables. So you can use another types of entry, like which is referred usually as a statistical regression. But I would advise against it because you have less power to generalize the results to the population. The results usually only confined to your sample. So for us, we have two blocks and we enter one variable we're controlling for in block 1 and another variable in block 2. The next things we need to choose are all the statistics we want software to compute for us. So if we'll go to statistics, we need to choose R-squared change. This will allow us to see how much additional variance the media pressure accounts for when we control for self-esteem. We want descriptive statistics. We want part and partial correlation, and we want Durbin-Watson test because Durbin-Watson test tests the assumptions, and we also want case-wise diagnostic because that's another test testing for assumptions. We press continue. We go to plots, and we want to put standardized predicted scores on the x-axis and standardized residual scores on the y-axis, and this one is to test for homoscedasticity. And we want to also look at the histogram to look at the distribution and probability, normal probability plots, which will also give us information about the distribution of our dependent variable, errors of the dependent variable. Continue, and If we'll go to Save menu, we can select Cook's distance to look at is there any outliers or influential cases that need to be removed from the data set. So continue, and we press OK. So the Cook's distance have computed, but I can't see my output. On Macs, sometimes SPSS hides the output and there is no way of seeing it. There we go, that's the output. Okay. So what the output contains, we have our descriptive statistics, and we see the mean for negative attitude to adverts, mean for self-esteem, and mean for media pressure. We also see our correlation coefficients between all three variables, and we can see that these correlation coefficients are all significant. And just as expected, self-esteem had a preventative, in a way, effect. Media pressure facilitated negative attitude, and self-esteem and media pressure also negatively correlated. So as your self-esteem goes up, your feeling of media pressure goes down. This table explains which variables were entered in a model. So we see model 1, also referred to sometimes as step 1, we only entered self-esteem, and in step 2 we only entered the media pressure scores. The model summary table explains how much variance each of the predictors explained in our dependent variable, and we can see that model 1, and in model 1 we only had self-esteem, explained 13.2% of variance in negative attitudes towards the advert, and it was significant. Now, model 2, this value for the R squared is the total of the variance explained in the dependent variable when we have both self-esteem and media pressure scores in the model. To see how much unique variance media pressure explains, we want to go to the R squared change, to here. So you see self-esteem, because it was the first one in the model, it secured its variance, but this R squared change gives us the value that media pressure explains additional 7.9% in 7.9% of variance in negative attitude towards adverts, and we can see that it was significant. The next table is ANOVA, which basically tests your regression model against the null model. So the null one would be predicting scores on attitude towards the advert solely based on the means. So in this case, the mean is 2.14, and the idea is everyone would dislike the advert to the same extent. But what this model tests is if we know levels of self-esteem, can we make a more accurate prediction about the attitude to the advert? And the model is significant, which means yes, self-esteem is better to gives us an additional accuracy in prediction. And same happens with the model 2 when we have our two variables in the model. So the next bit, what we have is the regression coefficients. So we have our standardized beta regression coefficient. And we can see self-esteem was entered first in the model, and its regression coefficient is exactly the same as its Pearson's regression coefficient. So 0 order represent Pearson regression coefficient. And it is significant predictor. What happens when we enter to look at how much additional contribution does media pressure make, we can see, so this one, the model 2 in this instance, is pretty much the same table as you would get if you just did multiple regression. So you would see two variables competing for the variance explained in the dependent variable. So the only kind of interesting difference between just doing multiple regression and doing hierarchical is this additional variance explained by the predictor controlling for another variable. And what we see, as these two variables are competing with each other for the variance, the effect of self-esteem reduces, and we have the standardized beta coefficient for media pressure score that also kind of like different from its correlation. So again, we're starting slowly to remove shared variance between self-esteem and media pressure from explanations of each variable. So based on this one, the next important table we want to look at is the histogram. And histogram allows us testing the assumptions, so we can see that the errors are of our dependent variable or residuals are skewed positively, but they still resemble normal distribution in a way, and our sample is quite large. This graph, PP plot, also tests exactly the same thing, the distribution of errors, and ideally you want all the dots to land on this black line. It's in a way, the closer the dots are to the line, the better. But when you work with the real research data, you always have some deviations. So in this case, okay, it's not ideal, but it's more or less acceptable. And then we have our homoscedasticity plot, so we can examine that variance across different levels of predictors is equally spread. So in terms of assumptions, so you use this graph to examine homoscedasticity. You use this graph and this graph to examine normality or distribution of your errors. And you want to use collinearity or tolerance statistics to look how variables in a model, like where the two predictive variables strongly correlate. In this case, it presents no problem. And you also want to look for this Durbin-Watson test, and the value should be between 1.5 and 2.5. So the whole statistics for Durbin-Watson test ranges from 1 to 4, and closer it is to 2, the better. So that one tests for independence of scores. This is information that you need to test the assumptions that you have for regression. In terms of reporting regression and important statistics for the actual regression test, you are interested in R-squared for the first step, R-squared change and their respective significance levels. You are interested in ANOVA for model 1 and for model 2, and you are interested in your regression coefficient with their respective t-values and their respective significance level. So those are the three tables from where you get your values to report the results of hierarchical regression. And this is it.